Hi, I'm Anthony Kirincich. I'm a physical oceanographer at the Woods Hole Oceanographic Institution. My research focuses on oceanic exchange between the coastal zone and the deep ocean due to atmospheric winds on a variety of scales. However, over the past 8 years, I've become involved in both the science and observational efforts related to the growing offshore wind energy industry. We have the unique distinction that 6 of the first large lease areas to be established in the U.S. and 3 of the first major wind farms that will be built in the U.S. are in our backyard. And because we are local to the development, we've been working with the industry and impacted ocean stakeholders to both serve as a scientific collaborator as well as to develop and transition new technologies for their use and benefit. Most of my own efforts have focused on understanding the wind as a fuel and the wind as a design criteria using our local coastal observatory. The map of estimated mean annual wind speed shown here is based on a series of modeling and validation efforts made by the National Renewable Energy Laboratories. But we really need more information to understand the seasonal and event scale variations, atmospheric turbulence, and extreme events that local wind energy sites will have. That is exactly what we've tried to do. Hui built and maintains the Martha's Vineyard Coastal Observatory and its Air-Sea Interaction Tower, pictured here, as a research platform not only for air-sea interactions, but also a wide range of ocean and climate-focused research priorities. However, it has also been highly useful for the growing wind energy industry in the U.S. The ACIT is the only Met tower in the eastern U.S. suitable for detailed air-sea interaction studies, and since 2016, we've collected industry-validated hub height wind observations, as well as other Met ocean observations at the tower, along with the basic science research that it's traditionally been used for. These data are unique in that they are publicly available, both in real time and via data archives, for researchers and industry folks alike to use, and at the end of the day, for the public's benefit. They've also been highly utilized as such. As an example, ISO New England, our local grid operator, did a study of potential wind energy output using our data that showed an incredibly high capacity factor for wind energy installations in the area, or how close to its maximum output an installed system could actually operate. From a more scientific focus, the data has been used to document issues that numerical models of the atmosphere will have in predicting hub height winds during times of increased stratification, as well as the extreme differences in background turbulence that wind turbines will see in the U.S. based on seasonal and event scale variations in the local winds. These ACIT-based observations are being used to serve as a LiDAR buoy validation location, the only such location in the U.S. that is pre-permitted for validations that are required by the industry. These activities will also serve as an anchor point for the upcoming Department of Energy-sponsored Offshore Wind Forecast Improvement Project. This is the third such project like this, and the first one that will be carried out in the offshore environment. It's a collaborative effort that unites us at Hui and our colleagues at a number of research universities with the national labs of the Department of Energy and NOAA. With a suite of surface and profiling buoys, land-based sites with radars and other large scanning systems, and flux profiles at the ACIT as well as a similarly instrumented barge deployed offshore, this effort will collect a massive data set of atmospheric and oceanic conditions within and surrounding our local lease areas in the hopes of doing exactly what the name suggests, improve our collective ability to forecast winds within wind energy resource areas. We've focused on this regional array because the ocean adds complexity to forecasts for offshore wind due to changes in roughness and momentum and heat transfer that can happen on time scales of hours to days and horizontal scales of tens of kilometers in coastal regions. This snapshot of co-located observations of sea surface temperatures and ocean surface currents shows how within the U.S. lease areas these properties can vary dramatically over the scales of kilometers, smaller than the lease areas themselves. The dense observational array that we'll deploy, along with high-resolution remote sensing and model products, will allow the impact of some of these processes on offshore winds and energy to be understood. Finally, one of the things that has fascinated me over the past few years is how interdisciplinary the science of offshore wind energy actually is. In addition to what I've described here, there's been significant effort in a range of related science areas, from understanding hurricanes for their design requirements for blades and foundations, advanced testing of new sensors both for the atmosphere and the ocean, as well as a host of biological, geological, chemical, and robotics issues that are far beyond this session. I like to call these gatherings of research efforts and infrastructure ocean testbeds for energy and climate because in combination they have the ability to address critical problems at the interface of the ocean and atmosphere, which make up our climate system, both for the energy industry and our broader continued use of these coastal areas.